Hey everyone, I'm Mihaela, and I'm excited to talk to you about our work on a continuous time model of gradient descent dynamics and instability in deep learning, presented at TMLR. This is joint work with my collaborators Yan Mu, Chong-Pi Kim, and Benoit Deron. So let's start with a summary of our work. We start with the principal flow, a new continuous time flow modeling the behavior of gradient descent. Unlike existing flows, the principal flow can capture instabilities observed empirically with gradient descent. We then take this novel understanding and produce DAL, an approach to setting the learning rate of gradient descent to control instabilities. We can then amend DAL so that we can control the stability generalization trade-off, that is to have a little bit more instability, but obtain more generalization. So let's first talk about our setting. So our goal is to analyze gradient descent updates aimed at minimizing function E. We're going to assume that function E is parameterized by theta, which has parameter dimension D. Throughout the talk, H denotes the learning rate. So if we want to analyze gradient descent, we have two approaches in doing so. The first one is the discrete time approach. That is, we directly analyze the gradient descent updates. This has an advantage of looking directly at what we want and accounting for the learning rate, but in practice, it tends to be a little more challenging to devise discrete time proofs. An alternative is to use continuous time approaches. Continuous time approaches analyze an underlying continuous time system, and they tend to be a little bit easier analytically. However, some flows, like the original flow that we can think of when thinking about gradient descent, which is the negative gradient flow, do not account for learning rates. So that means they cannot explain any behavior that depends on learning rate. Moreover, following the negative gradient flow always decreases the loss function, which we know is not the case with gradient descent. The approach that we're going to take here is a continuous time approach, but we're going to hope to find a new continuous time flow which can capture some of the observed instabilities and also depend on the learning rate. Let's start by looking at the existing continuous time flow. So I've already mentioned the negative gradient flow, which moves in continuous time in the direction of the negative gradient, hence the name negative gradient flow. Now, as I've said previously, the negative gradient flow, from which we can obtain gradient descent through Euler discretization, is a very useful tool for analysis. However, it doesn't capture learning rate dependent behaviors of gradient descent. To solve parts of that issue, David Barrett and Benoit Deron introduced implicit gradient regularization and what we will call implicit gradient regularization flow, which depends on the learning rate by adding an extra term. So it has the negative gradient in the modified in the vector field, and it has a term which depends on the learning rate, h/2, and then the Hessian of the loss function applied to the gradient. And they're able to show that they can produce learning rate specific behaviors by analyzing the implicit gradient regularization flow. However, both the negative gradient flow and the IGR flow have certain limitations, specifically around instability. So for example, if we have a quadratic landscape and we have a valley, we see that gradient descent can oscillate on the two sides of the valleys. This is what the plot on the left-hand side is showing. However, both the negative gradient flow and the IGR flow go straight towards the local minimum. We can see a similar example here on the right-hand side with the banana function. So our goal is then to find a flow that can capture some of these instabilities present in gradient descent. And to do so, we are going to use backward error analysis. So we are also going to aim to find another flow and modify this flow. We are often going to call the modified flow, which in backward error analysis is constructed as follows. We have new vector field, which again contains the negative gradient, and some additional terms which are constructed such that the difference between one gradient descent update and the continuous time flow after one update is of h to the n plus 2. So remember, h is the learning rate. So that is, we can control the error in learning rate between this modified flow and gradient descent. And to do so, we have to find these correction terms, these correction functions, fi, which will depend on E and its derivatives. And we've already seen F1 in the context of gradient descent, which is given by the correction term in the implicit gradient regularization flow. To give a little bit of intuition, the negative gradient flow has an error of h squared in learning rate, and the implicit gradient regularization flow reduces that and has an error of h to the third in learning rate. Our approach here is a little bit different. We look at all correction terms, that is, at all n, but we only restrict ourselves to terms which contain only a first order derivative in E, that is the gradient, or a second order derivative in E, that is the Hessian. So we don't look at higher order derivatives. In doing so, we obtain the principal flow. The principal flow depends on the Hessian through its eigenvalues and its eigenvectors. So lambda I here denotes the ith largest eigenvalue of the Hessian, and ui the corresponding eigenvector. And this leads to this form of the principal flow. So we sum over all eigendirections. We have the displacement in that eigendirection, which is given by this coefficient of the log 1 minus h lambda I over h lambda I, and the dot product between the gradient and the eigenvector in that direction. So this is the form of the principal flow. Now, just to start with some properties about the principal flow, it is exact for quadratic losses. So this means that the principal flow generalizes the negative gradient flow, which is exact for linear losses. That is, for the negative gradient flow to follow gradient descent exactly, we need the gradient to be constant on an area of space, which means that the loss has to be linear. The principal flow also generalizes existing backward error analysis flows by accounting for higher order and learning rates. Remember, as I mentioned, we look at all orders and learning rates, but we restrict ourselves only to terms which depend on the gradient and the Hessian. Unlike existing flows as well, the principal flow can be complex valued because this quantity log of 1 minus h lambda I over h lambda I can be complex depending on the value of h lambda I. Importantly also, performing stability analysis with the principal flow recovers some known properties of gradient descent. So existing flows like the negative gradient flow and the IGR flow will always predict that gradient descent will converge to a local minima. But we know that is not the case. So their stability analysis says that if we are around a local minima, gradient descent will go to that. But actually, performing a stability analysis of the principal flow, we cover some of the known properties that we are aware of, such as that for large learning rates, gradient descent will not converge to the local minima. So let's talk about certain quantities that are coming up as part of the principal flow that we will see are very relevant. One of them is the stability coefficient. And the stability coefficient is this coefficient in direction ui. So the stability coefficient itself has an index, and is this quantity that I've also mentioned previously, log of 1 minus h lambda I over h lambda I multiplied by the dot product between the gradient and the eigenvector. And to compare the principal flow with the negative gradient flow, we can also write the negative gradient flow in a similar form. So if we write the negative gradient flow depending on the eigendecomposition of the Hessian, we also have the dot product between the gradient and eigenvector. But instead of having this coefficient, which depends on eigenvalues, we have -1. So hence, again, the negative gradient. So when comparing the principal flow with the negative gradient flow, it's often useful to look in one eigendirection and to look at comparing the stability coefficient with -1. And again, the reason why this is also important is we know that following the negative gradient flow minimizes function E. So let's do a little bit of case analysis on how the principal flow looks like, especially in one eigendirection, depending on the relative value of h, the learning rate, and lambda I. So if h times lambda I is smaller than 1, or lambda I is smaller than 1 over the learning rate, The stability coefficient is real valued and negative, which is similar again to the negative gradient flow. And as we see in the simple example that we show here, there's again no imaginary component. And in this example, there's straight convergence to the minimum. Now, there is another case where lambda I is between 1 over h and 2 over h. Now, the stability coefficient in that eigendirection is complex, but it will have negative real part. So some oscillations can occur due to the imaginary part, but in that direction, the function E is still largely being minimized. Now, there's also the unstable complex case where lambda I is greater than 2 over h. Here, the stability coefficient is complex with positive real part. So now this is, again, in the opposite direction of the negative gradient flow, in the direction of minimization of E. And in the case of quadratic losses, this is the divergent case. So let's start with some small examples. And since I mentioned here again quadratic cases, remember that the principal flow captures gradient descent exactly in the quadratic case. So when we see oscillations or on the valley, the principal flow will capture that, and it will also capture divergence behaviors of gradient descent. Now, if we look at small neural networks where we can simulate the principal flow, we also observe that the principal flow captures gradient descent better than existing flows, as long as the number of steps in gradient descent is small. Because remember, the principal flow can be complex valued in the unstable cases, and there's nothing ensuring that the iterates will be real when many steps are being used, so the error can accumulate. However, while we cannot simulate the principal flow for large neural networks, because that would be computationally prohibitive, since simulating a flow for even one gradient descent steps requires taking many small steps to simulate a continuous time approach, and each step would require doing a full eigendecomposition of the Hessian. This can be problematic in practice. But what we can do is use the principal flow to estimate certain scalar quantities, which are more amenable to implementation in practice. And what we do is that we show that we can capture the dynamics of the dot product between the gradient and the leading Hessian eigenvector using the principal flow much better than existing flows such as the negative gradient flow and the IGR flow. So we show here that across learning rates for relatively large networks, such as a VGG model trained on CFAR10, that the principal flow prediction is much closer to the perfect prediction. So if we have like a perfect oracle, compared to the negative gradient flow and the IGR flow. Now, I'm going to switch a bit to talk about a phenomenon that has been observed recently in deep learning. The term edge of stability was coined by Cohen and al. In their excellent work. The authors do a very thorough empirical study showing that if we train neural networks with full batch gradient descent, what happens is that the leading eigenvalue, lambda 0, keeps growing steadily, after which it reaches 2 over h. And then instability occurs, and there's an oscillation around 2 over h, and that's also where loss instabilities occur. So to ask whether the principal flow is a good model for neural networks around the edge of stability area, we start again with a small neural network. We have a 5-layer MLP with 10 units each, where we can simulate the principal flow exactly. And we observe that in the edge of stability area, the principal flow captures the dynamics of gradient descent locally, again, for one iteration, better than existing flows. And it does so both by having a smaller error to its predicted parameters and gradient descent parameters, but also existing flows tend to predict that the loss is going to go down, while the principal flow can also predict that the loss doesn't always go down in training for large learning rates, and especially around the edge of stability area. Importantly, the principal flow tells us also something because of the stability coefficient. So if we look at the stability coefficient for the leading eigenvalue, it has this quantity log of 1 minus h, lambda 0 over h lambda 0. Remember, if lambda 0 is greater than 2 over h, as is the case around edge of stability, then this stability coefficient will be positive. However, the stability coefficient also tells us about this important quantity of the dot product between the gradient and the leading eigenvector. If this dot product is 0, we will not observe any instability because the stability coefficient itself will be 0. And we show an example here that is observed actually in training, where lambda 0 is greater than 2 over h, substantially so, but no instability in the loss function is observed, and the loss keeps steadily decreasing. And that is because the stability coefficient that we show here in the bottom row is 0. It is 0 because the dot product between the gradient and the leading eigenvector is 0. So to understand instabilities, we cannot look only at the largest eigenvalue lambda 0, though that certainly is a very important component, but also at the dot product between the gradient and that eigenvector. Similarly, we show in the case of a ResNet 18 training on CFAR 10 that stability coefficients are greatly related to the observed instabilities that we see. But more than that, remember, the stability coefficient is something that we can only estimate at gradient descent iterations because we cannot simulate the principal flow fully for large neural networks. But what we can do, and what the principal flow tells us, is to look at some simpler flows that gradient descent will resemble in certain areas of space. And this is the really fun part, which is we know that if lambda 0 is greater than 2 over h, all stability coefficients are going to be negative, so we can look at the behavior of the negative gradient flow. If lambda 0 is greater than 2 over h, we can also look at the behavior of the positive gradient flow, where we just swap the sign to go into a positive direction according to the eigenvectors. And what we observe is that the behavior of these flows in an area is also relevant towards the behavior of gradient descent. So for example, here on the right-hand side, we see a lot of instability in gradient descent, both in terms of loss changes and leading eigenvalue changes. Of course, the stability coefficient is rather large in that area, but also when we look at the positive gradient flow, there's a lot of changes there. And we see, for example, the red dots here. On the top panel, there's a lot of changes in lambda 0, which get reflected in the changes in the gradient descent. Now here also, we can contrast this with the left-hand side, where, again, that local landscape is less unstable, and then we see that that also gets reflected in the behavior of gradient descent. So we've seen how there's instability in gradient descent and how we can use the principal flow to understand that a little bit, but also the principal flow reveals an important quantity, which is this Hessian applied to the gradient and its connections to instability. And indeed, if we look at, we're aiming to find regions of the space where the principal flow, which captures, again, instabilities, is the same as negative gradient flow. That condition is that this quantity, the Hessian applied to the gradient, is 0. So if we're in the region of the space where this happens, the principal flow is the same as the negative gradient flow. But remember, the principal flow is exact for quadratic functions. In the case of neural networks, it will not be exact, and there are terms that we are missing when using the principal flow to model gradient descent dynamics. But what we can do is actually talk about the difference between gradient descent and the negative gradient flow, which is what we can call discretization error, or we call discretization drift. And we can approximate that. And we know that we can write this error as h squared over 2, and then the Hessian applied to the gradient as a set of parameters which we don't know in the neighborhood of the gradient descent iterate. So what's really interesting here is that this total drift, again, which captures the error between gradient descent and the negative gradient flow, is what will also cause instabilities, because remember, following a negative gradient flow decreases the loss function. And from this result, we can also say that actually, if the Hessian applied to the gradient is 0, gradient descent follows the negative gradient flow. So in those areas of training, we can really speed up because instabilities are not likely to occur. Of course, we can then use this information and try to test it empirically in the case of neural networks to see how good these approximations are. And this is what we do next. So we approximate the drift. We do that by simulating the negative gradient flow for one gradient descent iteration. So we do many steps of the negative gradient flow. We do one gradient descent step, and we estimate the difference in parameters there. And we compare that with our approximation, which is given by the learning rate squared over 2, and then the Hessian applied to the gradient. Again, because we don't know the exact parameters for which this is exact, we use the gradient descent its parameters. Nonetheless, we see a remarkable resemblance. We show here on the top plot some examples where we look across training, and we see very similar behaviors between the drift. So that is the error between gradient descent and the negative gradient flow and our approximation. But we also see this in the bottom plot, that there is a very high correlation between them across learning rates, across data sets, and in general in training. So we have now found an approximation of this drift. And the next question is, how can we use it in training? And I've already hinted at the fact that, well, when the drift is small, we can speed up training because it's unlikely to have instabilities. Now, an intuitive then way is to say, well, let's set the learning rate inverse proportional to the drift. And this is one thing that we try. This is what we call DAL, with a small difference here that we divide by the gradient norm. So not only the drift estimation is used. And the reason for that is that we want the overall parameter update to still be proportional to the gradient norm, because that's a useful quantity to have. Now, if we use this approach, which we call drift adjusted learning rate, or DAL for short, we see that it's actually quite stable in training, and it can learn rather quickly as well. So it just adapts according to the local landscape and slows down training when it needs to be slowed down and speeds it up when it can be sped up. Now, so far, we have talked only about training performance, training instabilities, because we're interested in optimization. But we have seen again and again in deep learning, and there's really great results in literature showing that actually larger learning rates lead to better generalization. So one idea that we had here, well, now we can control the drift directly, and we can speed up and slow down using DAL. But if we make DAL more or less sensitive to the drift, we should be able to see more or less generalization. And this is exactly what we tried. So for example, if we make DAL a little bit less sensitive to the drift, not to slow down so much if it needs to, and we use DAL 0.5, so we take the square root of our previous quantity, we observe not only that it's relatively stable and trains quickly on the training loss, but it also performs very well on test accuracy across data sets. So that's it in terms of the principal flow and DAL. In terms of future work, we actually think that there's a lot more that can be done here. We think that there are continuous time flows that can be useful beyond the principal flow. And we actually show preliminary evidence that certain non-principal terms can have a stabilizing effect in training. So please have a look at that if you're interested. There's also been a lot of work recently, a lot of great work in the literature at specializing continuous time flows to the neural network structure, because there's something very specific, neural network specific, when it comes to gradient descent dynamics. And we would like to specialize the principal flow also to the neural network structure. But also DAL actually is a very intuitive approach. It says where you have a lot of drift, try to slow down, and otherwise you can speed up. And we think that can be integrated with other optimization methods. And we show in the paper some preliminary successful results with momentum where DAL can be integrated with it as well. So that's it. We introduced a continuous time flow, the principal flow, which is able to capture instabilities observed in gradient descent. And we then use this understanding to introduce DAL-P, an approach to stabilize gradient descent training. Please do check out the paper as well, as it contains more insights and experiments, as well as additional references to the literature. Thank you.